Okay, this is not an example, but I just wanted to make it just a quick little discussion regarding resistivity and how it depends on temperature. There are two formulas. Here's a formula that relates the resistivity and how it would be affected as you increase the temperature. And if you'll notice from this formula, this is the original resistivity. This is a constant that depends on the atomic structure of the metal, so it depends on the type of material, and that's the change in temperature. The little zero here means, or O, that means the original resistivity and the original temperature. So as you can see here, the resistivity is directly proportional to the change in temperature. As you increase the temperature, the resistivity increases. And if you recall, resistance is equal to resistivity times length times area. So as you increase the temperature and the resistivity increases, then the resistance of the material itself will increase. So you don't need to know the working problems with this, but you do need to realize that resistance is directly proportional to the temperature. So as you increase the temperature of a wire, that will increase the resistance. So when we use Ohm's law, where the resistance is remaining constant, remember that voltage versus current graph in Ohm's law, where we have a linear relationship. If you have a metal like tungsten that is heating up and is starting to increase in temperature, then the resistance is actually changing. So we need to just keep that in consideration. We discussed down here with semiconductors are more complex materials and their resistivities actually decrease with temperature. And we have materials which I discussed earlier, superconductors, where the resistivity is zero when you bring it down to this low, very, very low temperature. And it becomes a basically a loop that conducts electricity with no resistance at all. So these are special situations that occur when you don't have metals. But just remember that resistance depends on temperature.